Would you trust a decision you can't explain? Every day, AI systems make decisions. In healthcare, autonomous driving, finance. But often, not even their creators know exactly why. At Fraunhofer HHI, we're working to change that by making models more transparent and trustworthy. In this video, we'll explore why AI models are often difficult to interpret, how layer-wise relevance propagation can be applied to a network, and how the resulting explanations help us understand the model's decisions. To begin, let's consider a simple example. We train a neural network to recognize animals in pictures. After having seen thousands of examples during training, it becomes impressively good and can classify animals with a high accuracy. Now, suppose we show the photo of a dog, the model predicts the correct breed and assigns it the highest score. Success, right? Well, maybe. Here's the problem. We don't actually know why it made that prediction. Did the network focus on the dog's pointy ears, the shape of its snout, or did it latch onto something totally unrelated, like the white background or the fact that the dog is sitting? Maybe, in all its training images, dogs just happen to be sitting, while other animals weren't. That doesn't mean every picture of a sitting animal should be classified as a dog. Just because a model is right, doesn't mean it got there for the right reason. This marks a fundamental shift from traditional programming. In classical software, we define the rules ourselves. For example, that pointy ears should indicate the class Corgi. Machine learning works differently. Instead of hand-coding rules, we feed the model data and answers, and it figures out the rules on its own. But unlike traditional code, they are hidden inside a black box. We can't simply read them. They are embedded in millions of parameters, spread across layers and activations. This makes it difficult to answer questions about the model's behavior, like which input features influence the decision. Why did the model choose a particular class? To address these questions, researchers have developed various so-called post-hoc techniques that can be applied to an already trained model. At Fraunhofer HHI, we developed layer-wise relevance propagation, LRP for short, a propagation-based method that explains neural network predictions by tracing how information flows through the model. LRP observes how inputs activate neurons at each layer during the forward pass, capturing the internal structure that led to the final prediction. It then redistributes the output score, propagating it backward through the network to highlight which input features were most influential. This results in an interpretable explanation of the model's decisions, where we will constantly highlight features that support the model's decision in red, and those that speak against it in blue. But what does such an explanation actually look like when applied to a real network? To find out, let's revisit our animal classification network. In this example, we'll be using a convolutional neural network. It takes an image with 3 color channels, red, green, and blue, as input. Through successive convolutional and pooling layers, the number of channels increases progressively, reaching up to 512 in our case. For clarity, in the visualization we only show 1 channel per layer, including the input. This simplifies things while still capturing the main idea. During the forward pass, each of those layers captures increasingly complex features, from simple edges to abstract patterns. After the final pooling block, the resulting feature maps are flattened into a one-dimensional vector and passed to a multi-layer perceptron which performs the final classification. So how does relevance flow through these different types of layers in our network? To answer that, we'll move backward, layer by layer, starting with the final 2. For now, we focus on a small subset of neurons, just enough to illustrate the key idea. Our goal is to share the Corgi neuron's relevance among the neurons in the previous layer based on how much each contributed to its activation. But how do we measure a single neuron's contribution? We can start by looking at the connection between them. The activation of the neuron multiplied by the weight of its connection to the Corgi neuron. This gives us a contribution score denoted as ZJK. On its own, this absolute number doesn't mean much. We need a proportion relative to all contributions in the layer. That's why we normalize it by dividing each set by the sum of all contributions to the neuron K. Optionally, we include the bias term. We can represent it as an additional input, neuron Z0, with a constant activation of 1 and a weight equal to the bias value. By doing that, we ensure that the total relevance is conserved across the network. We'll come back to that later. After observing, we move on to redistributing. But we haven't set an initial relevance to be redistributed yet. How we do that depends on what we want to explain. One possible choice, which we'll use here, is to assign all the relevance to the neuron for Corgi. We set its relevance equal to its activation and zero out all others. Each neuron in the previous layer now receives a share of this relevance, proportional to its contribution. In general, each neuron may receive relevance from multiple output neurons. The total relevance of a neuron J is therefore the sum of all relevance values propagated from neurons K in the layer above. But since we only initialize the Corgi neuron with relevance, we can ignore all other connections. Yet this simplicity won't hold in the next layers, where multiple paths must be considered. We mentioned conservation earlier. Here we can actually observe that the total amount of relevance remains constant across all layers. This happens because LRP redistributes relevance from one layer to the previous one without creating or discarding it. But while the total amount of relevance is preserved, it does not mirror activation. A neuron with low activation can still have a high relevance if it played a key role in the decision. As before, the bias also plays a role and needs to be added to the term so that the values balance out. This property is known as relevance conservation, and it plays a central role in ensuring that the explanation remains faithful to the model's prediction. Up to this point, we focused on the linear connections. But you may wonder if we've overlooked something crucial: the activation functions, specifically the ReLU. How does relevance flow through nonlinearities like these? To answer this, let's first observe how ReLUs work. They are element-wise functions that take a single value, usually a weighted sum plus bias, and return either 0 or that value depending on whether it's negative or positive. Because of this one-to-one structure, relevance propagation is straightforward. If a neuron didn't activate during the forward pass, meaning its contribution was 0, it also receives 0 relevance. If the neuron did activate, so if the ReLU let the signal pass through, then the backward pass simply lets the relevance flow through as well, unchanged. This is known as the identity rule, and it applies to most element-wise operations with a single input and output. With the ReLU handled, we now return to familiar ground. Just like before, we redistribute relevance from the penultimate layer to the one before it, based on each neuron's weighted contribution.
As we zoom out and move further back through the network, we leave the fully connected layers behind and arrive at the final part of the convolution block. The relevance scores from the fully connected layer can now be directly mapped onto the pixels of our grid because those neurons were simply a flattened version of the feature maps. Now that we understand these maps as neurons, just like in the MLP, we can ask the same question. How does relevance flow through those max pooling layers? We start by observing the forward pass and computing how much each neuron in layer L contributed to a specific neuron K in the next layer. In the case of max pooling with the 2x2 window, the contribution comes from the single pixel, the neuron, that had the highest activation within that region. To propagate relevance backward through a pooling layer, we need a strategy for redistributing it among the inputs. One common approach is to uniformly distribute the relevance across all pixels in the pooling window, treating them as equal contributors. Another is the winner-takes-all strategy. The entire relevance is sent back to the pixel that stood out, while the others receive nothing. But pooling isn't where things begin. The values in the pooled feature map originally came from the convolution layers. How does relevance flow through them? Let's first observe the operation. Convolution applies filters to the inputs. These filters are just sets of shared weights that get multiplied with the pixels and summed. In the backward pass, we simply redistribute relevance locally, giving each pixel a share based on its contribution to the activation. After seeing how relevance moves through every type of layer in the network, we can now follow this trail all the way to the very beginning. At each step, a new relevance map is generated, gradually tracing the model's decision back through the network. As a result, we get a heat map of the input image. The areas lit up in red are the model's key suspects, the features that strongly pointed to a specific dog breed. These parts of the image carried the most weight when deciding for a Corgi classification. But what if the model had leaned the other way? What details spoke for a cat, and why didn't they carry enough weight? To find out, we apply LRP again to the network, this time starting at the cat output neuron, while setting all others to 0. The resulting heat map tells a story. Pointy ears, small paws, and the fluffy fur. These features activated the cat neuron. But the face, especially the eyes and snout, pushed the network away from a cat classification. So LRP transformed our black box prediction into a more transparent and interpretable explanation. This gives us a clearer picture of the model's reasoning. It relies on the dog's distinctive features instead of being misled by artifacts such as the background. So let's recap the explanation process. First, we observed. We ran a forward pass to the network to get the model's prediction. Then, we redistributed. We traced the predictions backward, propagating relevance scores step by step through fully connected layers, ReLUs, convolutions, and pooling layers, all the way to the input pixels. Finally, we revealed the decision, producing a heat map that highlights which parts of the image mattered most to the model. If you're curious to try this on your own models, there are great tools out there to assist you. Libraries such as Xanit and LXT for PyTorch or Investigate for TensorFlow and Keras allow you to apply LRP with minimal setup. And the applicability of LRP doesn't stop at convolutional neural networks. It's been extended to a wide range of architectures, including recurrent, graph-based, and transformer models. It's not limited to classification either. LRP has been applied to regression, time series prediction, and other tasks, often in high-stakes domains like cancer diagnostics. And more recently, LRP has been extended to decompose predictions into concept-specific explanations, offering insights not only into where a model is focusing, but what concepts it is relying on to make its decisions. Seen enough? Now head over to the LXT repository and run LRP on state-of-the-art architectures like large language models and vision transformers. Thanks for watching and happy exploring!